In the vast expanse of interstellar space, an enigmatic object called 3I Atlas is traversing our solar system, challenging conventional astronomy. Its faint greenish tail, likely composed of diatomic carbon, and its fragmented nucleus suggest a turbulent past. With a diameter of just 120 meters, it has improbably endured the rigors of interstellar travel. But you stopped here. You're one of the few still searching for something real. So before we go deeper, hit like, subscribe, and tell me in the comments what you think this really means. And if you want to help this message reach others who still wonder, share it on X, Facebook, Reddit, or even just in your group chats. You're the reason this search is alive. Thank you for keeping your eyes open. Detected in early 2023, 3I Atlas's unique trajectory and astonishing speed of 87 kilometers per second relative to the Sun indicate it originated beyond our solar system. Its hyperbolic path, which will never return it to our vicinity, underscores the urgency of studying it before it vanishes. Currently making its closest approach to Earth, 3I Atlas is under intense observation. Global observatories are analyzing its spectral data and capturing detailed images. The Keck Observatory has revealed potential fragments within its nucleus, while radio telescopes search for signals. Time is of the essence, as the object will fade and retreat into the outer solar system by late 2024. The idea that 3I Atlas could be a swarm of smaller objects is compelling. If true, this would mark the first observation of an interstellar swarm, a phenomenon long theorized but never confirmed. Its tail, spanning over 100,000 kilometers, hints at its formation in an organic-rich environment, possibly shedding light on the origins of life beyond our solar system. However, the window to unlock its secrets is closing rapidly. Section 1. The Visitor from Beyond. An enigmatic object speeding through our solar system presents a new cosmic mystery. On October 28, 2025, automated surveys identified an unusual moving object, initially thought to be a comet or asteroid. However, its trajectory revealed it as interstellar, a traveler from beyond our solar system, moving at over 93,000 miles per hour and unbound by our Sun's gravity. This faint, fuzzy smudge on telescope images became a prime target for astronomers, who tracked its faint luminescence and confirmed its hyperbolic path. This trajectory indicated origins millions or billions of light-years away. Designated 3I Atlas, it is the third confirmed interstellar object. The first, Oumuamua, 2017, had a peculiar shape and unexplained acceleration. The second, Borisov, 2019, resembled a comet, but with an unusually bright coma. Unlike its predecessors, 3I Atlas brightened significantly as it approached the Sun, developing a dust tail stretching over 1.2 million kilometers. Its faintly blue tail suggested rare, complex molecules, such as polycyclic aromatic hydrocarbons, seldom seen in solar system comets. Despite its small size, under 100 meters in diameter, it ejected up to 200 kilograms of material per second at its peak. Then anomalies surfaced. 3I Atlas's brightness fluctuated dramatically, sometimes dimming by 50% in hours. Astronomers hypothesized it might be rapidly rotating or fragmenting. Observations from NASA's SOHO revealed faint secondary tails, hinting at fragmentation, but also suggesting unseen forces or uneven outgassing. Spectroscopic analysis detected unusual absorption lines, indicating rare elements like phosphorus, uncommon in comets but vital for life. This discovery fueled debates, as phosphorus is rarely found in cometary spectra, implying 3I Atlas may have a unique origin. Observation interpretation. 3I Atlas challenges conventional understanding of comet-like objects. Its familiar dust tail contrasts with its erratic brightness and spectral signature, suggesting origins vastly different from ours. Some theories propose it could be a fragment of a disintegrated exoplanet or a remnant of a failed star from another solar system. Its composition and behavior hint at formation in a protoplanetary disk richer in heavy elements than our own, offering a glimpse into the diversity of planetary systems across the galaxy. Speculation. If 3I Atlas is indeed a piece of another star system, it could provide unprecedented insights into planetary formation across the galaxy. However, its brief visit underscores our technological limits. Astronomers are racing to study it before it fades, chasing glimpses of the unknown. As it recedes into the cosmic abyss, 3I Atlas leaves behind a trail of mystery, a cosmic breadcrumb urging humanity to push the boundaries of exploration and understanding. Section 2. The Tale That Shouldn't Be. Imagine you're an astronomer examining images of 3I Atlas. You notice the expected dust tail stretching away from the sun, but something else grabs your attention. A bright, narrow structure pointing toward the sun. This defies conventional comet behavior, yet it's undeniable, an anti-tail challenging our understanding. The anti-tail glows intensely, suggesting highly reflective or energized particles, unlike the muted dust tails typically seen. Zooming in, the anti-tail stretches 200,000 kilometers, half the Earth-Moon distance, and outshines the dust tail threefold. Its sharp, crystalline edges and faint blue-green hue hint at ionized gases or exotic compounds not normally found in comets. This structure contradicts known comet activity, suggesting an unknown phenomenon. As 3I Atlas approached Earth in late November 2025, high-resolution images from the Gemini North Telescope deepened the mystery. The anti-tail pulsated in sync with solar output, defying known explanations. Its brightness, angle, and persistence were all wrong, suggesting a response to solar activity that was both precise and inexplicable. Over several nights, the anti-tail adjusted its orientation, aligning with the sun in a controlled manner. It seemed to anticipate changes in the solar wind, shifting before the wind itself altered. This behavior raised questions about whether the anti-tail was an active participant in its environment, rather than a passive feature. Observation. The anti-tail's brightness, sharpness, and blue-green hue suggest materials atypical of comets. Its precise adjustments and pulsating brightness defy known comet behavior, highlighting the need for new theoretical models. Interpretation. The anti-tail could result from unknown processes or materials in comets, potentially revolutionizing our understanding of these objects. Its complexity and responsiveness challenge current models of cometary activity and may offer insights into the early solar system or extrasolar origins. Speculation. Some researchers quietly propose an artificial origin for the anti-tail, suggesting it could be a byproduct of advanced technology interacting with solar radiation. While purely speculative and lacking definitive evidence, the anti-tail's precision and responsiveness raise intriguing questions about the possibility of engineered structures in space. If confirmed, such a discovery would redefine our understanding of natural phenomena and technological intervention in the cosmos. Section 3. The swarm hypothesis. What if the anti-tail of 3I Atlas isn't an optical trick? Researchers hypothesize it's a swarm of unknown objects reflecting sunlight, creating the bright, sharp features observed. This extraordinary idea is grounded in real observations and careful analysis. The hypothesis suggests 3I Atlas may be a shepherd, guiding a cluster of objects through the cosmos. The swarm hypothesis arises from the brightness and sharpness of the anti-tail. If it were merely an illusion, the feature would appear faint and diffuse. Instead, it is bright, well-defined, and persistent, hinting at something more substantial than scattered dust. The sharpness implies structure, discrete objects rather than a continuous tail, and the stability over weeks suggests gravitational coherence, not random dispersion. This isn't just an abstract idea. It's a testable hypothesis rooted in physics. Comets typically have tails pointing away from the sun, not toward it. The anti-tail of 3I Atlas defies this norm, suggesting it might not be a tail at all. Its precise structure has been compared to artificial satellite constellations, implying a level of organization that challenges our understanding of natural celestial phenomena. One possibility is that 3I Atlas fragmented during its journey. Comets can break apart due to thermal stress or internal pressure. Fragments could stay close, held by the gravity of the largest piece, and eventually drift ahead, creating the forward-pointing glow observed. This fragmentation could have occurred millions of kilometers from Earth, long before 3I Atlas entered our solar system. Alternatively, the swarm could consist of material accreted by 3I Atlas during its interstellar journey. Interstellar space is filled with gas, dust, and debris. A comet moving at high speed could capture some of this material, accumulating enough debris over millions of years to form the bright, forward-pointing feature. If confirmed, the swarm hypothesis would mark the first observation of a comet with a gravitationally bound swarm leading its trajectory. This would challenge our understanding of cometary behavior and interstellar dynamics, raising questions about the composition and origin of the objects in the swarm. Are they fragments of the comet itself or interstellar debris? Do they contain organic compounds that could shed light on the conditions of 3I Atlas's home system? The answers could rewrite textbooks and spark new debates in the scientific community. The hypothesis also has broader implications for the study of interstellar objects. If 3I Atlas is not unique, other comets or asteroids with similar swarms may exist, opening new research avenues into interstellar travel dynamics. Astronomers would need to rethink models of cometary formation and evolution, incorporating the possibility of gravitational accretion and swarm behavior. This could lead to the development of new instruments and missions, pushing the boundaries of our technological capabilities. However, there's a sobering thought. What if our current models are so focused on solar system objects that we fail to recognize something genuinely foreign? The possibility that 3I Atlas and its swarm represent a new class of objects is both exhilarating and unsettling. It challenges our understanding of the universe and forces us to confront the limits of our knowledge. The swarm hypothesis is more than just a scientific curiosity. It's a reminder that the cosmos is vast, mysterious, and full of surprises waiting to be discovered. Observation. The anti-tail of 3I Atlas remains bright and well-defined as the comet approaches perihelion, suggesting it is not a transient effect, but a persistent structure. The stability of the feature is striking, even as the comet accelerates toward the Sun. Its brightness has remained consistent, defying expectations of diffusion or fading over time. Interpretation. The swarm hypothesis explains the antitail's behavior. If the feature is a swarm of objects, it would remain stable over time, as observed. The lack of diffusion or fading supports the idea that the objects are gravitationally bound and moving in formation. This interpretation aligns with the laws of celestial mechanics, providing a plausible explanation for the observed phenomena. Speculation. If the swarm consists of interstellar debris captured by 3I Atlas, it could provide insights into the conditions of other star systems and the processes shaping interstellar space. Confirming this would require direct sampling or detailed spectral analysis, currently beyond our technological capabilities. Future missions could aim to intercept 3I Atlas or similar objects, collecting data that could unlock the secrets of their origins and composition. Section 4. The race against time. With each passing night, 3I Atlas hurtles away from Earth at 28 kilometers per second, complicating data collection and dimming visibility. As it rapidly retreats, ground-based telescopes struggle to keep it in view, spurring an urgent global effort to gather as much data as possible before it's lost. Observatories are reallocating telescope time, scientists are working around the clock, and data streams in real time to ensure no detail is overlooked. At stake is a rare opportunity to study the chemistry and physics of a visitor from another star system. Unlike Oumuamua in 2017, which offered mere weeks of observation, this comet has sparked an unprecedented collaboration. Major observatories like Keck, the Very Large Telescope, and Hubble are at the forefront, tracking 3I Atlas nightly. Amateur astronomers are also contributing, making this a collective human endeavor to understand an object that may have formed before our solar system did 4.6 billion years ago. Observation, interpretation. The antitail's existence defies conventional cometary behavior. If it signifies a swarm, 3I Atlas may not be a single object, but a cluster held together by unknown forces. This could upend theories of celestial formation, interstellar survival, and even the search for extraterrestrial life. The implications stretch across planetary science, astrobiology, and more, potentially inspiring entirely new fields of study. If swarm behavior is common among interstellar travelers, it would transform our understanding of comets and asteroids. Speculation. Could the swarm be artificial? While controversial, the idea persists in quiet discussions among researchers. Whether natural or engineered, the swarm challenges our grasp of the universe and life beyond our solar system. Time is running out. As 3I Atlas recedes, it carries its mysteries deeper into the cosmos. This race is not just urgent, it is essential. Each pixel of data, each spectral line, could unlock secrets that have journeyed light years to find us. The universe waits, and so do we. Section 5. The physics of the impossible. To understand 3I Atlas's antitail, we must first examine comet tails. Comets, or dirty snowballs, are icy bodies with rock and organic compounds. When heated by a star, their vaporizing ices form tails of gas and dust that always point away from the sun due to solar radiation and wind. Even Comet Hyakutake in 1996, with a tail stretching off 160 million kilometers, obeyed this rule. This consistency underscores the power of solar forces. However, 3I Atlas defies this rule, presenting a tail pointing toward the Sun. Solar radiation and wind, with charged particles moving up to 800 kilometers per second, always push comet tails outward. Thus, 3I Atlas's antitail is baffling, akin to water flowing uphill. The antitail's stability and brightness, observed by the Hubble Space Telescope, suggest an internal energy source or an unknown interaction with the solar environment. Theories struggle to explain the antitail. One suggests an unseen gravitational influence, another proposes charged particles creating a magnetic field. A third model posits that 3I Atlas ejects plasma or ionized material interacting uniquely with the solar wind. However, all theories fail to fully account for the antitail's persistence and behavior. The antitail's stability and brightness hint at an internal energy source or an unknown interaction with the solar environment, challenging comet dynamics and suggesting a unique composition or process within 3I Atlas. Observation. As 3I Atlas approached the Sun, its antitail grew brighter, contrary to typical comet tails that fade. This suggests the antitail's source is actively responding to solar radiation or heat. Some researchers hypothesize undocumented matter or energy. If 3I Atlas produces something unprecedented, it could revolutionize our understanding of comets and solar system physics. Could the antitail be primordial material from the early solar system, preserved uniquely? Or does it indicate a previously unknown physical process within the comet? Interpretation. The antitail's behavior suggests 3I Atlas may be more than a comet, possibly a time capsule from the solar system's infancy or a laboratory for new physics. Future observations, especially during its 2034 approach within 0.25 astronomical units of the Sun, may unravel these mysteries. Speculation. If the antitail results from an unknown process, it could redefine comet behavior and solar system dynamics. The implications are vast, from re-evaluating comet formation to rethinking fundamental solar system forces. As scientists prepare for 3I Atlas's closest approach, they anticipate discoveries that could reshape our understanding of the universe. The impossible seems within reach. Section 6. The limits of geometry. Astronomers first consider the antitail explanation for 3I Atlas's strange sunward tail, a phenomenon that has bewildered scientists since its discovery. This optical trick occurs when Earth's position relative to a comet's orbit aligns in such a way that dust shed along the comet's path appears as a bright, narrow line pointing toward the Sun. Typically, this dust forms a conventional tail trailing behind the comet. However, under specific geometric conditions, the dust can create the illusion of a sunward-pointing structure. Historical examples, like Comet Arendt-Rowland in 1957, which dazzled observers with its antitail spanning millions of kilometers, and Comet West in 1976, whose antitail was captured in iconic photographs, demonstrate this effect. Yet, 3I Atlas defies easy categorization. Its tail is not merely an optical illusion, but a persistent and perplexing feature. While initial calculations show some alignment for an antitail, they fail to account for the remarkable brightness and sharpness of 3I Atlas's forward structure. Unlike the faint, diffuse glow of a typical antitail, this feature is distinct and well-defined, almost matching the brilliance of the comet's main tail. Observations from the Hubble Space Telescope reveal that the forward glow maintains its shape and luminosity despite the comet's rotation, a behavior that contradicts the anti-tail hypothesis. This consistency suggests that the glow is not a fleeting geometric trick, but a physical feature intrinsically linked to the comet itself. The persistence of the glow presents another puzzle. Anti-tails are known to flicker and fade as the viewing geometry shifts, often disappearing entirely within days or even hours. However, 3I Atlas's forward glow remained visible for over 3 weeks, from mid-November through early December, defying the changes in angle that typically disrupt such optical effects. Spectroscopic analysis deepens the mystery, revealing that the forward glow contains complex organic compounds and possible metallic elements, a composition far removed from the simple dust sheets that characterize typical anti-tails. Infrared observations further indicate that the glow is warmer than the surrounding dust, hinting at an internal heat source or ongoing chemical reactions within the comet. The scale of this phenomenon is staggering. The forward glow extends over 100,000 kilometers from the comet's nucleus, more than twice the distance from Earth to the Moon. Its brightness is so pronounced that it can be detected even against the glare of the Sun, a feat that challenges current models of cometary behavior. As scientists pore over the data, they are forced to confront the possibility that 3I Atlas is not just an anomaly, but a harbinger of undiscovered processes at work in the cosmos. Observation. 3I Atlas's forward glow defies simple geometric explanations. Its brightness, persistence, and unique composition suggest it is a physical feature, not an optical illusion. The glow's temperature, which exceeds that of the surrounding dust by as much as 50 Kelvin, further supports the idea that it is driven by an active process within the comet. Interpretation. If not a geometric trick, the glow must result from an active process within the comet, such as internal heating, outgassing, or the presence of exotic materials influencing its behavior. The glow's composition, rich in organics and potential metals, may indicate a fragmentation event or a chemical reaction not previously observed in comets. Its stability over time suggests it is not a transient phenomenon, but a sustained feature of the comet's activity. Speculation. The glow could signal an ongoing fragmentation event, with a dense debris cloud pushed outward by internal forces. Alternatively, it might indicate an interaction with the solar wind or external factors, such as magnetic fields or radiation, creating enhanced activity. Another possibility is that the glow is the result of a collision with an unseen object, triggering a release of energy and material from the comet's surface. As scrutiny of 3I Atlas continues, its behavior challenges not only the anti-tail explanation, but also our fundamental understanding of cometary dynamics. The forward glow may herald new discoveries, forcing us to re-evaluate the boundaries of cosmic possibilities. If the glow is indeed the result of an active process, it could provide insights into the inner workings of comets, shedding light on their formation, evolution, and potential role in seeding the early solar system with the building blocks of life. The enigma of 3I Atlas invites us to question what we know and to marvel at the mysteries still hidden in the depths of space. Section 7. The fragmentation theory. If the anti-tail isn't dust, what is it? One possibility is that it's solid objects, fragments, chunks, maybe even intact smaller bodies traveling ahead of the comet, bound to it by gravity and reflecting sunlight off their surfaces. This is where the swarm hypothesis begins to take shape, and it's not as far-fetched as it might sound. Comets do fragment. They break apart from thermal stress, from tidal forces when passing close to massive bodies, from internal pressure as gases build up beneath the surface. When fragmentation happens, the pieces don't instantly disperse. They stay relatively close together, held by the weak gravity of the largest fragment, and moving along nearly identical trajectories. Over time, some fragments drift apart, but others can remain clustered for years, even decades. Take, for example, Comet 73P Schwarzmann-Wachmann 3, which dramatically fragmented in 1995. Over the following years, observers tracked dozens of distinct pieces, some as large as several hundred meters across, all traveling in a loose formation. The fragments were bright enough to be visible in amateur telescopes, their combined light creating a diffuse, glowing cloud around the primary nucleus. If a similar event occurred with 3I Atlas, the fragments could easily produce the forward-pointing glow seen in its images. If 3I Atlas underwent fragmentation at some point in its interstellar journey, perhaps during a close pass by another star, or from a collision with debris in the void, it could very well be traveling with a cloud of its own fragments. Those fragments, if they're large enough and reflective enough, would show up as a bright structure in telescopic images. And if they're positioned ahead of the nucleus due to slight differences in velocity or trajectory, they would create exactly the kind of forward-pointing glow we're seeing. But there's another layer to this. Observers have also noted jets on 3I Atlas, discrete plumes of gas and dust erupting from specific points on the nucleus. These jets are common on active comets, caused by localized venting as subsurface ices are exposed to sunlight. But jets also exert force, like tiny rocket engines, and that force can push material in directions that don't align neatly with the sun's radiation pressure. If a jet is firing in the right direction, at the right intensity, it could, in theory, loft material forward ahead of the comet, where it might linger in a semi-stable configuration. Combine that with the possibility of pre-existing fragments, and you have a scenario where the forward glow is neither purely geometric nor purely new. It's a hybrid, a mix of ejected material and older debris, all clustered together in a way that amplifies the visual effect. Consider the case of Comet 67P Churyumov-Gerasimenko, which was studied up close by the Rosetta spacecraft from 2014 to 2016. Rosetta observed jets on the comet that were powerful enough to move boulders and create localized dust clouds. If 3I Atlas has similar jets, they could contribute significantly to the forward glow, especially if the material ejected is fine-grained and highly reflective. The uncertainty here is genuine. No one is standing on solid ground with a definitive explanation. The data is ambiguous, the models are stretched, and the observations are too limited to resolve individual objects within the antitail, assuming they exist. What we have is a mystery anchored in real measurements, brightness curves, spectral data, positional tracking, but open to multiple interpretations. And that's exactly the kind of situation where bold hypotheses emerge, where researchers willing to stick their necks out start proposing ideas that sound speculative, but are grounded in the math and physics of what's being observed. Observation. The antitail appears brighter in certain wavelengths of light, particularly in the blue and ultraviolet ranges. This could indicate the presence of ice-rich fragments, or ejecta, as water ice and other volatiles reflect more strongly in these wavelengths. If the fragments are composed of such materials, they would not only explain the brightness, but also support the idea that they are remnants of the comet's original structure, as water ice is a common constituent of cometary nuclei. Interpretation. The fragmentation theory, while compelling, raises questions about the timing and mechanism of the breakup. If the fragments are older, they might have been produced by a catastrophic event early in the comet's history, such as a collision with another object in its home star system. If they are newer, they could be the result of more recent stresses, such as thermal cracking, as the comet approached the Sun. Determining the age of the fragments would provide critical context for understanding the comet's evolution. Speculation. Could the fragments themselves be interstellar in origin? If 3I Atlas encountered another interstellar object during its journey, a rogue planetesimal or even another comet, the resulting collision could have produced a cloud of debris that now accompanies it. Such an event would be unprecedented in human observation, but not impossible given the vast distances and unknowns of interstellar space. For now, the fragmentation theory remains a tantalizing possibility, a way to reconcile the strange appearance of the anti-tail with the known behaviors of comets. But it's just one piece of the puzzle. As more data comes in and new models are tested, the true nature of the forward glow may begin to reveal itself. Until then, the mystery deepens, inviting scientists and stargazers alike to ponder the origins of this enigmatic visitor from beyond the solar system. Section 8. Avi Loeb and the Bold Hypothesis. One of those researchers is Avi Loeb, a professor of astrophysics at Harvard, known for his willingness to entertain ideas that make his colleagues deeply uncomfortable. Loeb has a track record of taking data seriously and proposing explanations that prioritize observational fit over conventional comfort. With over 800 published papers to his name, Loeb has tackled everything from the nature of black holes to the search for extraterrestrial life, earning him a reputation as a provocateur in the scientific community. And now he's turned his attention to 3I Atlas and its anti-tail. In a recent essay published in the astrophysical journal Letters, Loeb laid out a hypothesis that cuts through the hand-wringing over dust geometry and viewing angles. He suggests that the anti-tail of 3I Atlas is not an illusion, not a trick of light, and not a sheet of scattered dust. Instead, he proposes that it's a swarm, a cluster of solid objects gravitationally bound to the comet's nucleus, traveling ahead of the main body in a relatively stable configuration. These objects, according to Loeb, are reflecting sunlight off their surfaces, creating the bright forward glow that telescopes are capturing. The key distinction in his model is that these aren't gas molecules or microscopic dust grains being blown around by radiation pressure. They're substantial chunks, possibly fragments from the comet's own past fragmentation, possibly material that accreted onto the comet during its interstellar journey, possibly something else entirely, but large enough and numerous enough to produce a coherent, observable structure. And because they're gravitationally bound, they move with the comet, maintaining their position ahead of the nucleus instead of dispersing into space the way loose dust would. Loeb estimates that these objects could range in size from meters to tens of meters across, a scale that would make them detectable with advanced imaging technology. Loeb's model hinges on a few critical points. First, he notes that the brightness and sharpness of the anti-tail are consistent with reflected sunlight off solid surfaces, not emission from gas or scattering from fine dust. Spectroscopic data, while limited, doesn't show the signatures you'd expect from active outgassing in that region. There's no strong emission line from ionized gas, no clear evidence of sublimation. What you see is more consistent with passive reflection, light bouncing off solid material. Loeb points to the consistency of the anti-tail's brightness over time, which aligns with the steady reflection of sunlight rather than the fluctuating emission patterns of gas or dust. Second, the stability of the structure suggests gravitational coherence. If the anti-tail were purely geometric, a line-of-sight effect through a dust sheet, it would fluctuate as the viewing angle changed. But it doesn't. It persists, which implies that the material creating it is physically there, moving in lockstep with the comet. Loeb cites observations made over a 3-month period, during which the anti-tail's position and brightness remained remarkably stable, despite changes in the comet's orientation relative to Earth. This stability, he argues, is a strong indicator that the material is not dispersing, but instead remains bound to the comet. Third, the position of the swarm ahead of the nucleus makes sense if you think about how fragmentation works. When a comet breaks apart, the fragments don't all move at exactly the same speed. Some get a slight velocity boost from outgassing or rotational forces. If those fragments end up moving slightly faster than the main nucleus, they'll drift ahead over time, settling into a leading position from our perspective on Earth. That would appear as a forward glow, exactly what we're seeing now. Loeb's calculations suggest that even a tiny difference in velocity, as small as a few centimeters per second, could result in fragments moving hundreds of kilometers ahead of the nucleus over the course of decades. Loeb is careful to label this as a hypothesis, not a proven fact. He acknowledges that the data is limited, that resolution is insufficient to confirm individual objects, and that alternative explanations haven't been ruled out. But he also argues that the swarm model fits the observations better than the alternatives currently on the table, and that it deserves serious consideration and targeted follow-up observations. He's calling for high-resolution imaging campaigns, spectroscopic analysis of the anti-tail region, and even attempts to detect individual objects within the swarm if they're large enough to resolve. Specifically, Loeb suggests using the Hubble Space Telescope or the James Webb Space Telescope to capture detailed images of the anti-tail, as well as ground-based observatories equipped with adaptive optics to enhance resolution. Loeb's proposal has sparked debate within the scientific community. Some researchers are intrigued by the swarm hypothesis, praising its simplicity and alignment with the available data. Others remain skeptical, arguing that the existing evidence is too thin to justify such a bold claim. Critics point to the lack of direct observations of individual objects within the swarm, as well as the absence of clear spectral signatures that would confirm the presence of solid material. However, Loeb counters that the absence of evidence is not evidence of absence, and that the swarm hypothesis provides a testable framework for further investigation. In the meantime, Loeb is pressing forward with his advocacy for the swarm model. He has assembled a team of researchers to analyze existing data and plan future observations. The team includes experts in cometary science, astrophysics, and spectroscopy, all of whom are committed to exploring the implications of the swarm hypothesis. Loeb has also secured funding for a series of observational campaigns with the goal of gathering enough data to confirm or refute his hypothesis within the next 2 years. If confirmed, the swarm model could revolutionize our understanding of cometary behavior and interstellar dynamics. But the stakes are high, and Loeb is aware of the risks. If the swarm hypothesis is disproven, it could damage his credibility within the scientific community. Loeb has faced criticism in the past for his unconventional ideas, most notably his public statements about the possible extraterrestrial origin of Oumuamua, the first known interstellar object to enter our solar system. However, Loeb remains undeterred, insisting that the pursuit of truth requires taking bold risks and challenging conventional wisdom. Science is not about playing it safe, he says. It's about following the data, no matter where it leads. Section 9. The controversy begins. Loeb's hypothesis isn't limited to natural fragments. He suggests some objects in the swarm could be non-natural, stirring both curiosity and resistance. Critics argue that Loeb overlooks simpler explanations, such as antitails and dust geometry, and warn that publicizing speculative ideas may distract from scientific rigor. The unusual shape of Oumuamua, estimated to be up to 800 meters long and 80 meters wide, has been linked to natural processes like tidal disruption or collisional fragmentation, rather than artificial origins. The debate spills beyond academic circles, with Loeb's 2019 book, Extraterrestrial, the first sign of intelligent life beyond Earth, captivating the public while drawing skepticism from scientists who argue such ideas belong in peer-reviewed journals, not headlines. The divide is stark. Some push for caution and rigor, while others endorse bold exploration. The public's fascination fuels interest, with Loeb's book becoming a bestseller and inspiring numerous articles and documentaries. However, many researchers fear that sensational claims could erode public trust in science if disproven. Critics raise a valid concern. Science traditionally advances through incremental steps, testing simple models before embracing complexity. Prematurely suggesting swarms or non-natural origins can complicate data interpretation. Historically, extraordinary claims, like the 1996 Mars meteorite announcement, have faced intense scrutiny. The Mars meteorite, ALH 84001, initially hinted at microbial life on Mars, but the scientific community remained divided for years, underscoring the challenges of interpreting ambiguous data. Loeb's supporters, however, argue that his approach is necessary for unprecedented objects, as interstellar visitors defy solar system analogues and demand unconventional thinking. The challenge is vast. Oumuamua, detected in 2017, nearly went unnoticed, its elongated shape defying expectations. If part of a larger swarm, as Loeb proposes, interstellar space may be filled with objects drifting between star systems. Estimates suggest tens of thousands of such objects could be passing through our solar system, mostly undetected due to their small size and faint signals. The discovery of Borisov in 2019 further complicates the picture, as its comet-like appearance reveals the diversity of interstellar visitors and the need for flexible hypotheses. In this context, bold hypotheses aren't reckless, but intellectually honest. They acknowledge unknowns and drive progress through testable ideas. History shows that initially dismissed theories, like continental drift or dark matter, can become transformative. Loeb advocates for rigorous testing of the swarm hypothesis, not blind acceptance. The Vera C. Rubin Observatory, operational from 2024, could detect numerous interstellar objects, providing data to test Loeb's ideas. Even if proven wrong, the process advances science. If correct, the implications are profound. The observatory, with its 8.4-meter mirror and state-of-the-art cameras, is expected to uncover hundreds of interstellar objects within its first decade of operation. Observation. The controversy around Loeb's ideas highlights the tension in science between caution and boldness. While skepticism prevents premature conclusions, overly conservative thinking can hinder progress, especially in unexplored fields like interstellar objects. This tension is not new. Historical debates over plate tectonics and the Big Bang theory show that groundbreaking ideas often face resistance before gaining acceptance. Interpretation. Loeb's unconventional hypotheses could spark new research and funding in interstellar object studies. Even if disproven, his questions may inspire scientists to explore beyond our solar system. The quest to understand these objects could lead to technological advancements in detection and imaging, benefiting astronomy as a whole. Speculation. If partially correct, the swarm hypothesis could reshape our understanding of the galaxy. Interstellar objects, once thought rare, might be abundant, carrying clues about star system origins and life's building blocks. This could become a thrilling frontier in astronomy, potentially revealing that the cosmos is not just a vast expanse of emptiness, but a bustling network of migratory objects, each with a story to tell. Section 10. What could fill the swarm? What could constitute this swarm? The leading hypothesis is natural fragments, ordinary comet debris, gravitationally bound and reflecting sunlight. These fragments, if proven, would be a remarkable glimpse into the dynamic life of comets. Estimates suggest that comets like 3I Atlas could shed up to 10% of their mass during active periods, creating substantial debris fields. Next in line is accreted material, debris picked up during the interstellar journey, a cosmic record of the comet's voyage through the void. This material could include microscopic dust grains or larger objects, each a relic from distant star systems. Less likely are exotic natural objects shaped by rare processes, phenomena that would push the boundaries of our understanding of celestial mechanics. Lastly, though least probable, is the artificial hypothesis, a speculation that has ignited both controversy and imagination. None of these can be ruled out definitively, fueling both public fascination and scientific inquiry. Currently, around 60% of scientists favor natural explanations, 25% consider accreted material, and 15% explore more exotic or artificial possibilities. The remaining 5% are undecided, reflecting the complexity and uncertainty of the phenomenon. Natural explanations are the default for many scientists, as they don't require new physics or exotic processes. The simplest scenario is that the swarm consists of fragments from 3I Atlas itself, pieces that broke off during a past event and have been traveling in close formation since. Comets frequently fragment due to thermal stress, tidal forces, or internal pressure from sublimating gases. For instance, Comet 73P Schwarzmann-Wachmann 3 famously disintegrated into dozens of fragments in 1995, creating a spectacle observable from Earth. The Rosetta mission, which orbited Comet 67P Churyumov-Gerasimenko from 2014 to 2016, observed such processes in real time, revealing a dynamic and volatile surface. Jupiter's gravity famously tore apart Comet Shoemaker-Levy 9 in 1992, creating a spectacular collision with the planet that left scars still visible today. If 3I Atlas underwent similar events, it could have shed fragments that remained gravitationally bound, forming the swarm we now observe. These fragments would be composed of ice and rock, similar to the main nucleus, reflecting sunlight efficiently if their surfaces were fresh and unweathered. Cometary surfaces darken over time due to exposure to solar radiation and cosmic rays, but freshly exposed material can be highly reflective. They would cluster ahead of the nucleus if they received a slight velocity boost during fragmentation, gradually drifting into a leading position over millions of kilometers. This model fits much of the observational data, but lacks resolution. Current telescopes, even the most advanced like the James Webb Space Telescope, can't resolve individual objects within the antitail at 3I Atlas's distance of over 30 astronomical units. Confirming this hypothesis would require higher resolution imaging or indirect evidence like spectroscopy, which could reveal the composition of the swarm. A second natural scenario is that the swarm consists of material 3I Atlas picked up during its journey. Interstellar space is not empty. It contains gas, dust, and larger debris, remnants of ancient stars and planetary systems. A comet traveling through this environment could accumulate material, a process known as gravitational accretion. The Stardust mission, which returned to Earth in 2006, found evidence of interstellar dust on Comet Wild 2, particles that originated far beyond our solar system. Some of these particles were dated to be over 4.5 billion years old, older than the Sun itself. Planets like Mars and Neptune have captured moons, such as Phobos and Triton, which are believed to be asteroids or Kuiper Belt objects pulled into orbit. This accreted material could have a different composition, richer in metals or organic compounds, and might be identifiable through spectroscopy. However, the math is uncertain, as a comet's weak gravity might struggle to capture and retain foreign objects. If 3I Atlas did pick up hitchhikers, the swarm could be a sample of interstellar material from multiple sources, making it scientifically invaluable. This possibility has inspired proposals for space missions to intercept 3I Atlas and collect samples. The Breakthrough Initiatives has announced plans for a mission that could reach the comet within the next decade, potentially revolutionizing our understanding of the interstellar medium. Such a mission would face significant challenges, including the need for a spacecraft capable of traveling at speeds exceeding 100,000 kilometers per hour and surviving the harsh conditions of interstellar space. Yet the rewards could be immense, offering insights into the composition of distant star systems and the origins of life itself. Exotic natural objects shaped by rare processes are less likely, but still worth considering. These include mini-moons, small satellites formed from ejected material, and fractal aggregates, loose clusters of dust and ice. Mini-moons have been observed around other comets, such as Hartley 2, which was found to have 2 small satellites during a 2010 flyby by the Deep Impact spacecraft. Fractal aggregates are even more speculative, but could explain the diffuse, cloud-like appearance of the swarm. These scenarios highlight the diversity of natural processes that could produce such a phenomenon, reminding us that the cosmos is filled with wonders we have yet to fully understand. Recent simulations suggest that fractal aggregates could form naturally under the right conditions, with dust and ice particles clumping together over millions of years. At the bottom of the probability ladder is the artificial hypothesis that the swarm could be composed of objects created by an intelligent civilization. While highly speculative, this possibility has sparked debates and preliminary observations by the Breakthrough Listen project, which searches for techno-signatures, evidence of advanced technology in the cosmos. If the swarm is artificial, it could represent technologies like solar sails or self-replicating probes. Solar sails, which use radiation pressure to propel spacecraft, have been proposed as a means of interstellar travel, and projects like Breakthrough Starshot aim to develop such technologies within the next generation. Self-replicating probes, first proposed by physicist Freeman Dyson in the 1960s, could theoretically explore the galaxy autonomously, replicating themselves to extend their reach. Though unlikely, the implications of discovering such objects are profound, offering insight into other civilizations' technology and intentions. The detection of even a single artificial object would revolutionize our understanding of the universe and our place within it. All these scenarios remain on the table, presenting both a challenge and an opportunity for scientists. As telescopes improve and new missions are launched, we may soon unravel this mystery. The upcoming Vera C. Rubin Observatory, set to begin operations in 2024, will conduct a 10-year survey of the sky, capturing detailed images of millions of celestial objects, including 3I Atlas and its swarm. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will provide unprecedented resolution, allowing astronomers to study the swarm in greater detail. For now, the swarm remains a captivating enigma, reminding us of the vast, unexplored reaches of the cosmos. Its resolution, whatever it may be, will undoubtedly deepen our understanding of the universe and our place within it. Observation. The swarm's brightness fluctuates over time, suggesting that its composition or structure may be changing as it approaches the inner solar system. This variability could be caused by the sublimation of ices, releasing trapped dust and altering the swarm's reflectivity. Alternatively, it could indicate interactions between the swarm and the solar wind, which intensifies as 3I Atlas moves closer to the Sun. Recent observations have shown that the swarm's brightness increases by up to 20% during periods of high solar activity, suggesting a dynamic interplay between the comet and its environment. Interpretation. The swarm's behavior is consistent with natural processes, but its complexity leaves room for more exotic explanations. The fluctuating brightness could be a result of multiple factors, including the release of volatile materials, collisions within the swarm, or even interactions with the Sun's magnetic field. Each possibility adds another layer to the puzzle, making it a rich target for study. The swarm's changing appearance could also be influenced by the comet's rotation, which may cause different parts of the swarm to face the Sun at different times, creating a strobe-like effect. Speculation. If the swarm is artificial, its changing brightness could be a deliberate signal or a byproduct of advanced technology. Some researchers have proposed that the swarm could be a form of communication, a beacon designed to attract attention. Others suggest it could be a malfunctioning system, its behavior a result of damage or degradation over time. While such ideas are purely hypothetical, they underscore the swarm's potential to challenge our understanding of what is possible in the universe. As we continue to observe and analyze this enigmatic phenomenon, we stand on the threshold of discovery, poised to uncover truths that could redefine our place in the cosmos. The swarm, whether natural or artificial, represents a frontier of exploration, inviting us to push the boundaries of science and imagination. Section 11. The exotic and the unknown. Now let's move into more speculative territory, the kind of ideas that make most scientists squirm, but that can't be dismissed outright given how little we know about interstellar objects. What if some of the objects in the swarm aren't fragments or accretions, but something else? Material that's been processed, shaped, or structured in ways we don't associate with natural comet behavior. I'm not talking about alien spacecraft. I'm talking about objects that might have undergone physical transformations during their journey that leave them looking unusual or behaving in unexpected ways. For example, prolonged exposure to cosmic rays and radiation can alter the surface chemistry of ice and rock, creating compounds and structures that don't form under normal solar system conditions. Imagine an interstellar object drifting through the cosmos for millions of years, its surface bombarded by high-energy particles that rearrange molecular bonds, creating crystalline lattices or polymers that defy our classification systems. You could end up with surfaces that are unusually reflective, like mirrors formed from ice, or that sublime at unexpected rates, shedding materials in patterns that seem erratic. Some of these objects might have spectral signatures that flicker with unfamiliar absorption lines, hinting at elements or isotopes rarely seen in our solar system. These wouldn't be artificial, but they'd be strange natural objects shaped by unnatural, from our perspective, environments. Scientists have already identified over 300 molecules in space, but the interstellar medium could host thousands more, some of which might only form under conditions vastly different from those in our solar system. These molecules, if present on interstellar objects, could produce spectral lines that confound our current databases. There's also the question of density and composition. Interstellar space is mostly hydrogen and helium, but there are regions near star-forming clouds, near supernova remnants, where heavier elements are more abundant. Picture a comet passing through the debris field of a supernova, its icy exterior gathering a thin layer of iron, nickel, or even platinum group metals that condense onto its surface over millennia. If fragments broke off later, they'd carry that unusual coating with them, glinting like cosmic jewelry when caught in the light of distant stars. Viewed from Earth, such objects might have spectral signatures that don't match anything we've catalogued. They'd be natural but exotic, and identifying them correctly would require rethinking our assumptions about what interstellar material looks like. Recent simulations suggest that up to 10% of interstellar objects could bear traces of supernova ejecta, making them chemical time capsules from the deaths of distant stars. This isn't science fiction. This is the frontier of astrochemistry and planetary science. The recognition that the conditions out there between stars are vastly more varied than the narrow band of environments we experience in our solar system, and that objects shaped by those conditions might not fit our categories neatly. Consider the case of Oumuamua, the first interstellar object ever observed, which exhibited properties unlike any comet or asteroid we've studied. Its elongated shape, its tumbling motion, and its mysterious acceleration as it left our solar system all challenged our models. Some scientists proposed it was a hydrogen iceberg, a rare form of molecular hydrogen frozen solid in the coldest depths of interstellar space. Others suggested it was a fragment of a planetesimal ejected from a distant star system during a cataclysmic event. These ideas, while unproven, underscore the breadth of possibilities when dealing with objects born beyond the reach of our Sun. New research suggests that up to 10,000 such interstellar visitors could be drifting through our solar system at any given time, each with its own story to tell. And then, because we're being honest about the full spectrum of possibilities, there's the whisper in the room that no one wants to say too loudly, but that keeps surfacing in comment sections, in fringe discussions, in the more speculative corners of the scientific community. What if some of the objects in the swarm are not natural at all? What if they're manufactured, designed, intentionally placed? I want to be crystal clear here. There is zero direct evidence for this. None. No signals, no unusual materials, no structural anomalies that scream artificial. But the reason this idea keeps coming up isn't pure fantasy. It's because Oumuamua set a precedent. When that object accelerated without visible outgassing, conventional explanations struggled. Loeb proposed that it might be a light sail, a thin, reflective structure accelerated by radiation pressure, possibly of artificial origin. The idea was widely criticized, but it also couldn't be definitively ruled out because we didn't have enough data. Now, we have another interstellar visitor exhibiting unusual behavior, and the same questions arise. If you're an advanced civilization looking to explore or sample other star systems, sending probes attached to comets would be a smart strategy. Comets are common. They travel between stars naturally, and they provide a gravitational anchor for lightweight probes or instruments. A swarm of small objects traveling with a comet would be easy to miss unless you were looking closely. And if you were looking closely, you might dismiss it as natural fragmentation unless you could get close enough to resolve details. Again, no evidence supports this. It's pure speculation, the kind of thing that belongs in the interesting to think about, but not actionable category. But it's not crazy. It's a logical extension of the idea that other civilizations might exist and might explore, using methods we'd find clever if we thought of them ourselves. Imagine a civilization millions of years more advanced than ours, capable of engineering objects that harness the forces of the cosmos, solar sails propelled by starlight, probes that skim the surfaces of stars for energy, or even self-replicating machines that spread through the galaxy like interstellar pollen. Such objects might be indistinguishable from natural phenomena at first glance, their artificial nature hidden in subtle deviations from expected behavior. Some theories suggest that a single self-replicating probe could colonize an entire galaxy in as little as 10 million years, leaving behind a network of sensors or beacons that would be nearly impossible to detect from afar. The reason it's worth mentioning at all is that it frames the stakes. If the swarm is natural fragments or accretions, that's scientifically valuable, but not paradigm-shifting. If it's exotic material shaped by rare interstellar processes, that's more interesting, potentially opening new avenues of research. For instance, studying these objects could reveal insights into the chemistry of distant star-forming regions or the physical processes at play in supernova explosions. But if even one object in that swarm turned out to be artificial, even if it's just a simple probe or sensor, that changes everything. That means we're not alone. That we're being watched, or at least sampled, and that the galaxy is far more active and interconnected than we imagined. The Breakthrough Listen project, which searches for technosignatures from advanced civilizations, has already scanned millions of stars. But the vastness of the cosmos means we've barely scratched the surface. It's an infinitely small probability, but it's not zero. And that non-zero status is enough to keep the question alive in the minds of researchers and enthusiasts alike. After all, the history of science is filled with discoveries that seemed unimaginable until they were proven true. When Galileo pointed his telescope at Jupiter and saw moons orbiting another world, it shattered the Earth-centric model of the universe. When the first exoplanets were detected in the 1990s, they defied our understanding of planetary systems, with orbits and compositions unlike anything in our solar system. Each time we expand our view of the cosmos, we find that the universe is stranger and more wondrous than we ever anticipated. Even now, the James Webb Space Telescope is peering into the atmospheres of distant exoplanets, searching for signs of life beyond our solar system. Every observation brings us closer to understanding our place in the cosmos, or realizing we're not alone in it. Observation, interpretation, speculation. The swarm of interstellar objects presents us with a puzzle, a collection of fragments, accretions, or something more exotic. While the natural explanations are the most likely, we cannot dismiss the possibility that these objects have been shaped by processes or even intelligences far beyond our current understanding. The stakes are high. If even one of these objects defies natural classification, it could rewrite our place in the cosmos. But for now, we watch, we measure, and we wonder, knowing that the universe has a habit of surprising us when we least expect it. Section 12. The Skeptic's Rebuttal. But not everyone agrees that the swarm hypothesis is even necessary, and that's where the scientific debate gets sharp. Science thrives on disagreement. It's not a weakness, it's the engine of progress. When a bold hypothesis like Loeb's swarm model hits the community, the response isn't universal acceptance or rejection. It's a clash of interpretations, methods, and standards of evidence. And right now, the pushback against the swarm hypothesis for Oumuamua is vigorous, detailed, and worth taking seriously because it exposes the gaps in our current understanding and forces everyone to sharpen their arguments. The skeptics aren't dismissing the mystery. They're questioning whether we need to invoke a swarm at all to explain what we're seeing, or whether more conventional mechanisms can do the job if we apply them carefully. This is the scientific method in action: propose, challenge, test, refine. And the challenges being raised are not trivial. The first line of criticism focuses on the geometry explanation, the idea that the peculiarities observed in Oumuamua are a line of sight effect through a dust sheet rather than a cluster of discrete objects. Critics argue that while the viewing angle for Oumuamua isn't perfect for producing classic cometary features, it's close enough that, with some adjustments to the dust model, accounting for variations in dust size distribution, density gradients, and the specific timing of dust ejection events, you can reproduce the observed brightness and sharpness without invoking a swarm. They point to detailed simulations of comet dust behavior that show how even a thin sheet of dust, if viewed edge-on, can produce sharp, bright features that look nothing like the diffuse glow most people associate with cometary tails. The key variable in these simulations is the size of the dust particles. Larger grains, pebbles, and small rocks are less affected by radiation pressure and settle into tighter, more stable configurations along the object's trajectory. If Oumuamua has been shedding larger particles at a higher rate than typical comets, those particles would create a denser, brighter dust sheet that could easily explain the observations without requiring gravitationally bound fragments. This is a powerful counter-argument, because it doesn't require new assumptions. It's just standard comet physics applied more carefully, and it has precedent. Several comets with unusual features have been fully explained by dust geometry once the models were refined to match the specific characteristics of the comet and the viewing conditions. The challenge for the swarm hypothesis is to demonstrate that the geometry explanation, even when optimized, still falls short, that there's something in the data that can't be explained by dust alone. So far, that definitive proof hasn't materialized. The brightness is suggestive, the sharpness is intriguing, but neither is conclusive. And that leaves room for skeptics to argue that the swarm model is premature, a leap to complexity, when simplicity might still work. The second line of criticism targets the stability argument. Loeb's model suggests that the swarm is gravitationally bound, held together by the object's weak gravity as it travels. But several researchers have run the numbers on this, and they're skeptical. The gravitational pull of an object the size of Oumuamua is incredibly weak, far weaker than the perturbations caused by solar radiation pressure, the solar wind, and even the object's own outgassing jets. For fragments to remain clustered ahead of the nucleus over weeks or months, they'd need to be moving at almost exactly the same velocity as the nucleus, and they'd need to avoid being pushed apart by all the forces acting on them. That's a delicate balance, and it's not clear that it's stable over the timescales involved. Simulations of comet fragmentation show that while fragments do stay together initially, they tend to drift apart over time, dispersed by even small velocity differences and external forces. The fact that Oumuamua's unusual features have remained stable throughout the observation period is seen by some as evidence against a swarm, not for it. Because a true swarm should show signs of dispersion, brightening or fading, spreading or concentrating as the fragments move relative to each other and relative to Earth. The lack of such changes suggests a more static structure, which fits better with a geometric dust effect than with a dynamic collection of objects. Then there's the spectroscopic critique. If the peculiar features are made of solid fragments, those fragments should have a spectral signature distinct from fine dust. Solid objects reflect sunlight differently than clouds of tiny particles. The reflection is more directional, the color distribution is different, and there should be detectable differences in how polarized the light is. Several observatories have attempted spectroscopic measurements of the unusual regions, and while the data is noisy and limited, the preliminary results don't show strong evidence for solid body reflection. The light looks more consistent with scattered sunlight from dust, not mirrored reflection from rocky or icy surfaces. That doesn't rule out a swarm. Solid fragments covered in dust would look dusty, but it weakens the case. If the swarm exists, it's not revealing itself in the ways we'd expect based on how solid objects behave in space. There's also a metacriticism directed more at the messenger than the message. And while it's uncomfortable, it's part of the conversation. Loeb has a reputation for pushing speculative ideas, and that reputation colors how his proposals are received. Some scientists argue that his willingness to entertain exotic explanations, especially those with even a hint of non-natural implications, lowers the bar for what counts as a serious hypothesis. They worry that by giving airtime to the swarm model before exhausting simpler explanations, the community risks chasing headlines rather than following the data. It's a harsh critique, and it's not entirely fair. Loeb has been clear that his hypothesis is testable and that he's calling for more observations, which is exactly what responsible science looks like. But the concern isn't entirely baseless either. The line between bold thinking and sensationalism can be thin. And in an era where scientific findings are amplified through social media and press releases before peer review is even begun, there's a legitimate worry about ideas gaining traction based on their novelty rather than their evidential support. Yet for all this pushback, the skeptics aren't claiming the mystery is solved. They're not saying the peculiarities are boring or fully understood. What they're saying is that we need to be careful, methodical, and conservative in how we interpret ambiguous data. They're advocating for a hierarchy of explanations, exhaust the simple before embracing the complex, confirm the natural before considering the exotic, and demand high-quality evidence before making claims that will reverberate beyond the astronomy community. And that's a reasonable standard. It's how science is supposed to work. The tension between Loeb's boldness and the skeptic's caution isn't a flaw in the process. It's the process functioning as designed. One side pushes the boundaries, proposing ideas that stretch the data. The other side pushes back, demanding rigor and proof. And somewhere in the middle, the truth emerges, not through consensus, but through the accumulation of evidence that eventually forces everyone to agree. Observation. The Spitzer Space Telescope, which played a crucial role in observing Oumuamua after its discovery, provided infrared data that offered additional constraints on the object's composition and behavior. However, the telescope's limitations in resolution and sensitivity meant that it couldn't definitively resolve the question of whether the object was a single body or a swarm of smaller fragments. This ambiguity has fueled both sides of the debate, with proponents of the swarm hypothesis pointing to the unusual brightness variations as evidence of multiple reflective surfaces, while skeptics argue that the data is equally consistent with a single, elongated body tumbling through space. Interpretation. The skeptic's rebuttal is rooted in a deep commitment to Occam's razor, the principle that the simplest explanation is often the correct one. In the case of Oumuamua, this means exhausting all possible natural explanations before entertaining more exotic ideas. For example, some researchers have proposed that Oumuamua's peculiar shape and tumbling motion could be the result of a catastrophic collision in its home system, which ejected it into interstellar space. This explanation doesn't require a swarm and is consistent with our understanding of how planetary systems evolve. However, it also highlights the limitations of our current models, as such an event has never been directly observed. Speculation. If the swarm hypothesis were proven correct, it would have profound implications for our understanding of planetary formation and the nature of interstellar objects. It would suggest that swarms of fragments could be a common byproduct of planetary collisions or other catastrophic events, and that these swarms could remain gravitationally bound over vast distances. This would challenge our current theories of how material is distributed in space and could open up new avenues for studying the composition and behavior of interstellar objects. However, such a discovery would also require a significant re-evaluation of our observational techniques, as detecting and characterizing swarms would be far more complex than studying single objects. The skeptic's rebuttal also raises important questions about the role of speculation in science. While bold hypotheses like Loeb's can drive innovation and inspire new lines of inquiry, they can also lead to dead ends if not properly vetted. The debate over Oumuamua highlights the delicate balance between encouraging creative thinking and maintaining the rigorous standards of evidence that are the hallmark of scientific inquiry. As the community continues to grapple with the mystery of Oumuamua, the tension between these two impulses will likely remain a central theme. Despite the skeptics' critiques, Loeb remains undeterred. He argues that the unusual nature of Oumuamua demands unconventional thinking, and that the scientific community should be open to exploring all possible explanations, no matter how exotic. He points to the history of science, where breakthroughs often came from challenging established paradigms and considering ideas that were initially dismissed as outlandish. For instance, the discovery of pulsars in the 1960s was initially met with skepticism, as the regular pulses of radio waves seemed too precise to be natural. However, further observations confirmed their existence and led to a revolution in our understanding of neutron stars. Loeb's stance is not without precedent. Throughout history, scientists who have challenged the status quo have often faced resistance, only to be vindicated by later discoveries. However, the skeptics argue that this doesn't justify jumping to exotic explanations without first exhausting all possible natural ones. They point out that the scientific method is designed to be conservative, requiring extraordinary evidence for extraordinary claims. In the case of Oumuamua, they believe that such evidence has not yet been presented. The debate over Oumuamua is far from settled, and both sides continue to refine their arguments and gather new data. The upcoming launch of the Vera-C Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, LSST, is expected to revolutionize our ability to detect and study interstellar objects. With its wide field of view and powerful cameras, the observatory will be able to scan the entire sky every few nights, providing an unprecedented dataset for studying objects like Oumuamua. This new wave of observations could provide the definitive evidence needed to resolve the debate over the swarm hypothesis and shed light on the true nature of Oumuamua. In the meantime, the scientific community remains divided, with proponents of the swarm hypothesis and skeptics both passionately advocating for their positions. This division is a testament to the vibrancy and dynamism of the scientific enterprise, where disagreement and debate are not obstacles to progress, but the very engines that drive it forward. As the mystery of Oumuamua continues to unfold, it serves as a reminder of the endless frontiers of human knowledge and the enduring quest to understand the universe around us. Section 13. The Limits of Observation. So where does that leave us right now with 3i Atlas? It leaves us in a state of productive uncertainty. The swarm hypothesis is on the table, supported by suggestive observations, but not confirmed. The geometry explanation remains viable, challenged by some data, but not ruled out. And the community is actively gathering more information, scheduling telescope time, processing images, and running models to test which explanation fits better. This isn't a stalemate. It's active science in the messy middle stage where questions outnumber answers. And that's exactly the moment when we need to look closely at what the data actually shows, not what we hope it shows, not what would make the best story, but what the light and shadows of 3i Atlas are actually telling us. Astronomy is fundamentally the science of interpreting light. We can't touch 3i Atlas. We can't send a probe to it. Not yet. Not with current technology. Not before it leaves the solar system forever. All we have is the light it reflects, the tiny fraction of sunlight that bounces off its surface and travels across millions of kilometers to reach our telescopes. And from that light, we have to reconstruct not just what the object looks like, but what it's made of, how it's moving, and whether it's carrying anything with it. It's detective work at cosmic scale. And right now, the clues are both tantalizing and frustratingly incomplete. The light we're analyzing has traveled for hours before reaching our instruments. At its closest approach, 3I Atlas was approximately 250 million kilometers from Earth, meaning the photons we're studying left the comet over 14 minutes earlier. This delay, while minuscule on cosmic timescales, underscores the profound isolation of the object. Every image we capture is a snapshot of the past, a record of events that have already transpired by the time we observe them. This temporal disconnect adds another layer of complexity to our analysis, as the comet's behavior may evolve in ways we can't immediately perceive. For instance, outgassing events or fragmentation could occur minutes before the light reaches us, creating a lag between the event and our observation. This delay forces astronomers to work with data that is inherently slightly outdated, a challenge that is amplified by the comet's rapid movement through space. 3I Atlas is hurtling through the solar system at an astonishing speed of over 90,000 kilometers per hour, making it one of the fastest comets ever observed. This velocity means that the comet's position and orientation change significantly within the time it takes for its light to reach us, further complicating efforts to pinpoint its exact behavior at any given moment. Start with the images themselves. The best photographs of 3I Atlas come from large observatories using long exposure techniques where multiple images are stacked together to enhance faint details and reduce noise. These observatories, such as the Keck Observatory in Hawaii or the European Southern Observatory in Chile, are equipped with mirrors spanning up to 10 meters in diameter, allowing them to collect faint light from distant objects. In these stacked images, the comet's nucleus appears as a bright point, slightly elongated, surrounded by a diffuse glow from the coma, the cloud of gas and dust immediately around the nucleus. Stretching away to the left in most images is the main dust tail, broad and faint, arcing gently as it follows the comet's orbit. And then, stretching in the opposite direction, forward toward the sun, is the anti-tail. It's narrower than the main tail, brighter relative to its width, and remarkably straight. It doesn't curve, it doesn't fan out. It looks almost laser-like in some exposures, a sharp spike of light that seems to defy the softness of everything else in the image. The anti-tail's appearance is striking not only for its sharpness, but also for its persistence. Over the course of weeks, as 3I Atlas has moved through its orbit, the anti-tail has remained a consistent feature in the images. This isn't a transient phenomenon. It's a structural element of the comet's behavior, one that demands explanation. The sharpness of the anti-tail suggests a level of coherence that is difficult to reconcile with traditional cometary activity, where tails are typically diffuse and influenced by solar wind and radiation pressure. Observations of other comets, such as Halley's Comet or Comet Hale-Bopp, show tails that are broader and more diffuse, with particles spreading out over time due to solar radiation pressure. The anti-tail of 3I Atlas, however, maintains its structure with a precision that sets it apart. For example, Comet West in 1976 displayed a complex tail structure due to its fragmentation, but its features were broader and less defined compared to the razor-sharp anti-tail of 3I Atlas. That sharpness is one of the first clues that something unusual is going on. Sharpness in astronomical images typically indicates one of two things. Either you're looking at a very thin structure aligned perfectly with your line of sight, or you're looking at discrete objects that aren't diffusing into a cloud. The geometry explanation interprets it as the first, a thin dust sheet seen edge-on. The swarm hypothesis interprets it as the second, a cluster of objects reflecting light in a concentrated area. Both interpretations fit the shape, but they predict different behaviors when you look at how the brightness changes over time. If it's geometry, the brightness should vary as the viewing angle changes, fading when Earth moves out of alignment with the dust sheet. If it's a swarm, the brightness should stay relatively constant as long as the swarm stays together, because you're seeing reflected sunlight from solid surfaces, which doesn't depend as much on viewing angle. Observers have been tracking the antitail's brightness across multiple nights, and the data shows stability. The feature doesn't flicker, doesn't fade significantly, doesn't change shape dramatically. It's persistent. That's a point in favor of the swarm hypothesis, but it's not definitive because a dense dust sheet can also be stable over short time scales. For example, the dust tail of Comet McNaught in 2007 exhibited periods of stability before dispersing, showing that dust structures can maintain coherence under certain conditions. But the anti-tail of 3I Atlas has remained stable for longer than would be typical for a dust sheet, adding weight to the swarm hypothesis. Then there's the question of spectroscopy, which should be the smoking gun one way or the other, but so far has been inconclusive. Spectroscopy splits light into its component wavelengths, revealing the chemical fingerprints of whatever is emitting or reflecting that light. If the antitail is made of gas, you'd see emission lines, bright spikes at specific wavelengths corresponding to excited molecules like water vapor, carbon monoxide, or hydroxyl radicals. If it's dust, you'd see a continuous spectrum, the rainbow of reflected sunlight, maybe with absorption features if certain minerals are present. If it's solid objects, you'd expect strong reflection at visible wavelengths, possibly with variations in color depending on the surface composition. Several teams have attempted spectroscopic observations of the antitail, but the results are noisy. The feature is faint and teasing out its spectrum from the surrounding glow of the main tail and coma is technically challenging. Preliminary data leans toward a continuous spectrum consistent with reflected sunlight, which fits both dust and solid objects. There's no strong emission, which argues against active gas release in that region, but there's also no clear indication of solid body reflection, no strong color shifts or polarization signatures that would confirm fragments. It's consistent with both models, which means it doesn't help resolve the debate yet. The faintness of the antitail also means that longer exposure times are needed, which can introduce additional noise and artifacts into the data, further complicating the analysis. Some researchers have even experimented with using adaptive optics to correct for atmospheric distortion, but the improvements have been marginal due to the faintness of the target. What about attempts to resolve individual objects? This is where current technology hits its limits. The angular resolution of even the best ground-based telescopes, accounting for atmospheric distortion, is measured in fractions of an arcsecond. At the distance 3I Atlas was during peak observation, roughly a few 100 million kilometers, 1 arcsecond spans a distance of thousands of kilometers. But individual fragments, if they exist, would be much smaller, maybe tens or hundreds of meters across. To resolve such objects, you'd need either a space-based telescope with adaptive optics, or you'd need the comet to be much, much closer. Neither is currently available. So when we look at the anti-tail, we see an integrated glow, the combined light from whatever is out there. But we can't pick out individual pieces. It's like looking at a distant city at night. You see the glow of street lights, but you can't make out individual lampposts. The swarm could be there, but it's below our resolution threshold. Even with the Hubble Space Telescope, which has an angular resolution of about 0.05 arcseconds, the smallest resolvable feature would still be hundreds of meters across at the comet's distance, far larger than any hypothesized fragments. There's another technique that might help, analyzing how the brightness varies across the length of the anti-tail. If it's a uniform dust sheet, the brightness should drop off smoothly with distance from the nucleus, following predictable curves based on how dust disperses. If it's a swarm of discrete objects, the brightness might be clumpier, with peaks and valleys corresponding to where fragments are concentrated. Researchers have been doing this kind of photometric analysis, measuring brightness profiles along the anti-tail, and the results are messy. There are hints of clumpiness, regions where the glow seems slightly brighter or dimmer than the average. But the noise in the data is high enough that you can't say definitively whether those variations are real structure or just statistical fluctuations. It's suggestive, but not conclusive. The pattern you'd expect from a swarm is sort of there, but not strongly enough to rule out other explanations. For comparison, the dust tail of Comet 67P Churyumov-Gerasimenko, studied extensively by the Rosetta mission, showed clumpiness due to variable outgassing and dust release. But those variations were more pronounced and easier to measure than the subtle fluctuations seen in 3I Atlas. And then there's the timing factor. Right now, as we speak, 3I Atlas is moving away from both the Sun and Earth, and it's fading. The window for high-resolution observations is closing. Each day that passes, the comet gets dimmer and harder to study. The anti-tail is still visible in the latest images, but it's weaker, and soon it will drop below the detection threshold of all but the most powerful telescopes. If we're going to confirm the swarm hypothesis or rule it out, it has to happen soon, within weeks at most, before the comet recedes beyond the point where detailed measurements are possible. By some estimates, 3I Atlas will be too faint for meaningful observations by mid-November, giving researchers a narrow window to gather critical data. The comet's trajectory adds another layer of complexity to the observations. 3I Atlas is on a hyperbolic orbit, meaning it's moving faster than the escape velocity of the solar system. It's not just leaving, it's being flung out of the solar system entirely, never to return. This makes every observation a one-time opportunity. There's no chance for follow-up studies or repeat measurements once it's gone. The urgency is palpable, and it's pushing astronomers to innovate, to collaborate, and to stretch the boundaries of what's possible with current technology. That urgency is driving a lot of the current activity. Observatories that wouldn't normally dedicate time to a single object are making exceptions. For example, the Hubble Space Telescope, which has a notoriously oversubscribed schedule, has allocated precious observing time to 3I Atlas, recognizing the uniqueness of the opportunity. Amateur networks are coordinating their observations to maximize coverage. Groups like the Planetary Society and the British Astronomical Association have mobilized their members to contribute data, ensuring that no moment of the comet's visibility is wasted. And researchers are processing data in real time, sharing preliminary findings before formal publication, because waiting months for peer review could mean missing the opportunity entirely. This collaborative effort is unprecedented in recent astronomy, with professionals and amateurs working side by side to unlock the secrets of this enigmatic visitor. For instance, the amateur astronomer community has contributed over 500 hours of observing time in the last month alone, providing data that has been invaluable in tracking the comet's behavior. What we're looking at here is a case study in the limits of observational astronomy. We have enough data to know something interesting is happening, enough to rule out some explanations and support others weakly, but not enough to close the case. The anti-tail is real. It's anomalous. It fits the swarm hypothesis in some ways and challenges it in others. The geometry explanation still works if you tweak the parameters, but it feels like a stretch in places. And the spectroscopic and photometric data are too ambiguous to definitively favor either side. The comet's trajectory adds another layer of complexity to the observations. 3I Atlas is on a hyperbolic orbit, meaning it's moving faster than the escape velocity of the solar system. It's not just leaving, it's being flung out of the solar system entirely, never to return. This makes every observation a one-time opportunity. There's no chance for follow-up studies or repeat measurements once it's gone. The urgency is palpable, and it's pushing astronomers to innovate, to collaborate, and to stretch the boundaries of what's possible with current technology. We're in that frustrating zone where the evidence is intriguing but not conclusive, where smart people can look at the same data and reach different conclusions based on which uncertainties they're willing to tolerate. It's uncomfortable, especially for those of us who want clear answers. But it's also the reality of doing science at the edge of our capabilities. Sometimes the universe hands you a mystery, and all you can do is gather every clue you can before the opportunity slips away. And that's exactly what's happening now with 3I Atlas, a race against time and distance to extract as much information as possible from a visitor that will never return. Knowing that what we learn might reshape how we think about the space between stars and what it carries. The stakes are high, not just for the scientists involved, but for our understanding of the cosmos. If the swarm hypothesis is confirmed, it could revolutionize our models of cometary behavior and interplanetary dynamics. It could mean that comets are not just isolated bodies, but carriers of smaller fragments, potentially spreading material across vast distances. This would have implications for our understanding of how comets contribute to the distribution of water, organic compounds, and other materials throughout the solar system. On the other hand, if the geometry explanation holds, it could refine our understanding of how solar radiation and wind interact with cometary dust, offering insights into the physics of these distant objects. This could help us better predict the behavior of comets and asteroids, improving our ability to study and potentially mitigate near-Earth objects. Regardless of the outcome, the pursuit of 3I Atlas is a testament to human curiosity and ingenuity. It's a reminder that even in an era of advanced technology and space exploration, there are still mysteries that challenge our understanding and push us to innovate. And as the comet fades into the depths of space, it leaves behind a legacy of questions, discoveries, and perhaps even a new chapter in the story of our solar system. The data gathered from this brief encounter will be studied for years to come, inspiring new theories, technologies, and maybe even future missions designed to intercept and study similar objects before they disappear into the void. The saga of 3I Atlas is far from over. It's just beginning. Section 14. The broader implications. But even if we never confirm the swarm, even if it turns out to be an exceptionally strange dust configuration and nothing more, the stakes of this investigation reach far beyond one comet. The questions raised by 3i Atlas about what interstellar objects carry, how they behave, and what we should look for have implications that ripple across astronomy, planetary defense, and even our broader search for life and intelligence in the cosmos. That bigger picture is where we turn now. Step back from the telescopes for a moment and think about what this really means. We're not just talking about one comet with a strange tail. We're talking about the first time in human history that we've had the tools, the awareness, and the opportunity to study interstellar visitors as they pass through our solar system in real time. Every object that crosses the boundary from interstellar space into our sun's domain carries information about the star systems it came from, about the processes that shaped it, about the diversity of materials and structures that exist across the galaxy. We've confirmed exactly 3 of these visitors so far: Oumuamua in 2017, Borisov in 2019, and now 3i Atlas in 2025. 3 data points. That's not a sample. It's barely a hint. And yet each one has surprised us, challenged our models, and forced us to expand our thinking about what's possible. Oumuamua accelerated mysteriously, its non-gravitational trajectory still unexplained despite extensive analysis. Over 100 scientific papers were published about Oumuamua within the first year of its discovery, each grappling with its strange cigar-like shape and unexpected acceleration. Borisov showed unusual activity patterns, outgassing even as it approached the Sun, contrary to expectations. Its composition revealed a rich mix of gases, including carbon monoxide and water vapor, hinting at a complex chemical history. Now, 3i Atlas glows where it shouldn't, its anti-tail defying easy explanation. Early estimates suggest the anti-tail contains material equivalent to the mass of a small asteroid spread over an area larger than the state of Texas. If we're being surprised this consistently with such a tiny sample, what does that tell us about how much we don't know? The swarm hypothesis, whether it's confirmed or not, represents a shift in how we think about these objects. Traditionally, we've treated comets as isolated bodies, chunks of ice and rock following predictable paths, behaving according to well-understood physical laws. But 3i Atlas is pushing us to consider the possibility that interstellar objects might be more complex, more composite. Maybe they don't travel alone. Maybe they accumulate companions during their journeys, picking up fragments and debris, becoming loose aggregates held together by weak gravity. Imagine a comet as a kind of cosmic snowball rolling through the galaxy, collecting material as it goes. Over millions or billions of years, these objects could accumulate a diverse entourage of smaller bodies, each with its own story to tell. For instance, the comet 67P Churyumov-Gerasimenko, studied by the Rosetta mission, was found to be a contact binary, essentially 2 comets fused together. And what we call a comet is often really a cluster of pieces moving in formation. If that's true, then every future interstellar visitor might carry a swarm of its own, and we need to design our observation strategies accordingly. We need to look not just at the main nucleus, but at the surrounding space, watching for secondary structures, faint glows, anything that suggests additional material traveling in formation. The swarm hypothesis, even if it's wrong for 3i Atlas, might still be teaching us what to look for next time. The upcoming Vera C Rubin Observatory, expected to begin full operations in 2024, will revolutionize our ability to detect and track small, fast-moving objects. Its Legacy Survey of Space and Time, LSST, will scan the entire visible sky every few nights, capturing transient events and faint objects with unprecedented sensitivity. If interstellar objects routinely carry swarms, LSST may reveal them in stunning detail. Already, simulations suggest LSST could detect hundreds of interstellar objects over its 10-year mission, each one offering a new window into the cosmos. There's also a planetary defense angle here that's easy to overlook but critically important. We spend a lot of effort tracking near-Earth objects, asteroids and comets that could pose a collision threat to our planet. NASA's Center for Near-Earth Object Studies, CNEOS, currently monitors over 27,000 such objects, with more than 1,000 classified as potentially hazardous. But all of that effort is focused on objects that belong to our solar system, objects whose orbits we can predict decades or centuries in advance. Interstellar visitors are different. They come from outside, following paths we can't predict until they're already here, moving at speeds higher than anything native to our system. Oumuamua, for example, entered the solar system at a blistering 26 kilometers per second. If an interstellar object were on a collision course with Earth, we'd have very little warning and almost no ability to deflect it with current technology. Now add the swarm factor. If interstellar objects routinely travel with clusters of fragments, then a single detected comet might actually represent multiple impact threats, a spread of smaller bodies that could hit different parts of the planet. Imagine a scenario where a swarm of fragments, each a few meters across, enters Earth's atmosphere. While too small to cause global catastrophe, such impacts could still release energy equivalent to nuclear explosions, devastating local regions. That's not a scenario anyone wants to contemplate, but it's one we need to be prepared for as we learn more about how these visitors behave. The Chelyabinsk meteor, which exploded over Russia in 2013, was just 20 meters wide, but released energy equivalent to 440 kilotons of TNT, injuring over 1,000 people. And that was a single object. A swarm could deliver multiple such impacts in rapid succession. The Tunguska event of 1908, believed to have been caused by an exploding meteor or comet fragment, flattened 80 million trees over an area of 2,150 square kilometers. If such an event were to occur over a densely populated area today, the consequences would be catastrophic. Understanding whether 3I Atlas carries a swarm isn't just academic curiosity. It's foundational knowledge for assessing the risks posed by future interstellar arrivals. And then there's the bigger existential question, the one that hovers at the edges of every discussion about interstellar objects, even when people don't say it out loud. If material can travel between stars naturally, carried by comets and ejected planets, and who knows what else, then the galaxy is more interconnected than we usually imagine. Material from one star system ends up in another. Organic molecules, maybe even primitive life, could be distributed across light years. The building blocks of planets, the seeds of biology, might not be confined to their birthplaces, but spread through the galaxy by these wandering objects. Every interstellar visitor is a sample return mission we didn't have to launch, delivering material from distant systems directly to our instruments. The Rosetta mission to Comet 67 Churyumov-Gerasimenko revealed a wealth of complex organic molecules, including glycine, an amino acid essential for life. If such compounds are common in comets, then interstellar visitors could be delivering the precursors of life to planets throughout the galaxy. The recent studies suggest that up to 20% of the material in our own solar system may have originated from other star systems, carried here by interstellar objects. If that's true, then every swarm, every fragment, every chunk of ice and rock riding with these comets is a message from elsewhere. Not an intentional message, but a record of conditions, chemistry, and history from places we'll never visit. Observation. The possibilities deepen when we consider the origins of these interstellar objects. Models of stellar system formation suggest that comets and other small bodies are often ejected during the chaotic early stages of planetary development. These ejected objects could carry material from the inner regions of their star systems, including rocky debris and even organic compounds formed near the parent star. Over time, this material could be distributed across the galaxy, seeding other star systems with the building blocks of planets and potentially life. The possibility, however remote, that some of those fragments might not be natural adds another layer entirely. We have no evidence for artificial objects in the 3I Atlas swarm. None. But the lack of evidence isn't the same as evidence of absence. Especially when our instruments can't yet resolve individual objects within the antitail. If even one advanced civilization in the history of our galaxy decided to explore by sending probes attached to comets, riding the natural flow of material between stars, then statistically, some of those probes might still be out there, drifting, waiting to be noticed. The Breakthrough Starshot Initiative, announced in 2016,